Newton's third law is useful when you have multiple objects and you want to use some aspect of the free body diagram of one object to understand something about the free body diagram of a second object. A simple example of this, we could put a box of mass, let's call it 4m, and we can attach it with a pulley, a frictionless pulley that a rope passes over to a box of mass m. And I could ask you, what's the acceleration of box m, for example? So in this case, I have two objects. I don't feel like I know a lot of information, but what I can do is go back to my Newton's second law, and I can treat both objects. I could start with box little m. So for box little m, I'd have a free body diagram that looks like weight points down, which is equal to mg, and tension would point up to the extent it exists. The string has tension. I'd circle box M. I don't see any other contacts, so that's it. Tension points up here because the string points up away from box little m. For box 4m, put a circle around it. We have remember, a frictionless table in this case. I could add friction, but it would go frictionless for this example. Well, in that case, I still only see one contact. Actually, sorry, I see two contacts. Gotta be careful. I touch the surface and the string. Tension points to the right in the string if it exists. And I have a normal force. And I'm going to assume that the box is not currently accelerating through the table. So I'm going to assume that the weight that the object has, that also points down, in this case, the weight would be equal to 4 mg, will be equal to the normal force, because those are the only two forces with vertical components. And since I do not expect this object to be accelerating vertically, F net y rather, should be 0. That means n must equal w. All right, so I have the free body diagram of both these. The way third law comes into play with interacting objects is the motion of these two objects is not independent. So what I can say is AM is necessarily going to be equal to A 4M. Why? Because they're attached by the string. If the little box moves an inch, the big box has to move an inch. So they have to have the same accelerations. That's the first thing you get for free from interacting object situations. The second thing is from Newton's third law. I push on you, you pull on me. In this case, the thing that's connecting the two objects is tension. So the tension applied to the little box and the tension applied to the big box has to be the same magnitude. Okay, so what we can do then is set up two second law situations where F net equals MA. So A is equal to F net over M. So little guy is then equal to F net applied to A, applied to little m rather, over M. Right? The mass of M, little m is M. And that's Newton's second law. So then it's just I have to put where F net goes. What would determine F net? Well, if it accelerates, it will accelerate down. And so it would be mg minus t over m. A 4m would be equal to F net 4m over 4m. So these are just subscripts on the top, but on the bottom, it's 4 times m is the mass of box 4m. All right, well, F net for 4m will be in the x component. The y component will not have a net force because AY for box 4M is 0. So that's just going to be equal to T over 4M, right? So now I have two different equations, but I know that the T and the A is the same in both. So I can change both of these to just be equal to A. That is the same for both boxes. Oh. And then what I can do here is have a set of simultaneous equations. Oh, man. Where I have two variables in each equation that is the same, which means I can solve for both through substitution. So for example, I could take from this bottom equation my knowledge that A is equal to T over 4M, put T over 4M where A goes. Now, since T over 4M is equal to A. And in that case, I could potentially solve for some things. I could solve for the tension, for example. How could I do that? Well, I can get rid of this M in the denominator and rewrite this as this. Right, that's taking the M across. And I could okay. And then finally, I could put this in terms of G or M or whatever. I could solve for the mass of the box, I guess. But I'd have to solve for it in terms of tension. I have to know something ultimately. But I could say something like G is equal to 1.25 times the tension over M, something like that. So then depending on what you're given, what you weren't given, you can represent any number of answers. But the point is, the main thing here is that two things you know through Newton's third law is that two objects that are interacting must share a common acceleration, and that the interacting force, once we identify it, has to be the same magnitude in both free body diagrams. I lost my train of thought a little bit with that coughing fit. I realized that the most likely thing you could solve for here, and notice I didn't give anything rather than this final thing I wrote over here. So you could actually use this to solve for the tension in terms of the weight of little box M. And that's just saying where we left off up here, where mg would be equal to 1.25 times the tension, solve for the tension, and you would find that tension is equal to mg over 1.25. Mg is just the weight of the little box. So the tension in this string would have to be 4/5 of the weight of the box. And so that means there would be an acceleration because in your free body diagram, the tension pointing up would be a little bit smaller than the weight pointed down.